Another form of an op-amp circuit is called the summing op-amp. We're going to work through how this one works. What's drawn here now is an inverting op-amp circuit with a single input. We're going to call this will be V, we'll call this VA for now. And we have V out. And we worked out how this worked before, where V out was a function of VA times the ratio of these two resistors. And now I'm going to add a little twist to this, and we're going to analyze a different kind of circuit. So I'm going to add another resistor right here, like this, and a second input. We'll call this VB. And so we'll have RA here. This will be RB. And we'll call this R feedback. And the question again is now, what is V out in terms of the inputs, VA and VB? We're going to use the idea of a virtual ground. Virtual ground. The idea of a virtual ground applies to most op-amp circuits, and it's a really useful way to simplify the analysis. And when we use a virtual ground, one of the things I like to do is just draw a little symbol here, like that, for my virtual ground. The virtual ground, as a review, if the voltage coming out of this op-amp is in a reasonable range, sort of plus or minus 10 volts or something like that, and because the gain of this op-amp is so enormous, on the order of 100,000 or a million, that means that when this is working properly, that these two voltages will be really close together. They'll be only microvolts apart at most. And because they're so close, we can just say, let's just say they're the same for the purposes of analyzing this circuit. And since this input is at 0 volts, this is at 0 volts, that means that this input is very close to 0 volts. So this node here we say is at a virtual ground. So let's move ahead. Let's analyze this circuit. And what we want to find is we want to find V out as a function of VA and VB. Let's see if we can do that. So looking at my circuit, the other thing I know about op-amps that's really important always is that the current going into an op-amp input is 0 or practically 0. And for the purposes of what we're doing here, we can treat it as 0. Right? So we have 0 volts on this node. We have 0 current going this way. So let's go after this current right here. Let's figure out what that is. So we'll call that I. And we can express I in terms of VA and VB and these two resistor values. So we can write I equals, now what is it? Well, we have IA here, and we have IB flowing here. That means that I equals IA plus IB. Right? And let me write IA and IB in terms of Ohm's law here. So we get I equals, what is IA? IA is this voltage divided by RA. And this voltage is VA minus 0 volts. So it's VA over RA. And now let's write down what's IB. IB, we look at this voltage here. This voltage is VB minus 0, or just plain VB over RB. All right, so that's one step. We've written this current in terms of what's going on the input side over here. Now, one thing we know, because this current is 0, we know what? We know this current is I. And if I is going into RF, we'll label the voltage on RF like that. So now let's write an expression for I in terms of RF and this voltage here. What is this voltage here? Well, let's look at the two ends. This is 0 volts on this node here, and on this side it's V out. So the current there, the current on that side equals, it's 0 minus V out, so minus V out divided by RF. That's Ohm's law for this resistor right here. Now we know that this current equals this current, so let's just set these two expressions together. So I'll do that over here. I can write minus V out over RF equals, let's look at this one, VA over RA plus VB over RB. Now we can get the final function. I'm just going to multiply through by RF on both sides, and we get V out equals, take the minus sign with us, minus RF over RA times VA plus RF over RB times VB. So that's our answer. That's V out as a function of VA and VB, the two inputs. And you can see that the resistor ratio, there's two resistor ratios here that are participating in the answer. So it helps to do a little special case of this. Let's let all the resistors be the same. So we'll say that RA equals RB equals RF. And just to pick a real number, we'll just say they're all equal to 10K ohms. And let's see what this becomes now. Now we have V out equals, we still have the negative sign. So this is some sort of inversion going on here. RF over RA is 1, so it's just VA. And RF over RB is 1, so this says VB. So this is what gives us the nickname for this expression, which is called a summing op-amp. Let's say I want to use my summing op-amp in an application where what I want is I want V out to equal, say, minus 2 times VA plus 3 times VB. Okay, this is what I want. How do I do that? So these two coefficients here are functions of the resistor values. That was our original expression up here. So what I want is RF over RA to equal 2, and I want RF over RB to equal 3. So I can pick values. It's the same RF, and so I get to adjust RA and RB in here. So I can pick component values. If I pick RF equals 12K ohms, then I can pick RA equals 6K and RB equals 4K. And that would give me the ratios I want, and that would implement this function here. So I'm going to go fill those out on the top schematic. We'll just write those in. And we'll go fill these in here. So what we said was RF was 12K. RA was 6K ohms. RB would be 4K ohms. And we've designed a circuit that implements our summing function. So this is a pretty useful op-amp circuit.